Hello there. We are going to move on to our next topic in gas laws. If you are following along from RHS, this is going to be topic 5 in your notes. If you're not from RHS, gas stoichiometry is the same everywhere, so you can still follow along. All right, so what in the world was stoichiometry? This was from our last unit of study. Stoichiometry was the method of calculation that relates quantities, remember that means numbers, of reactants and products. So in other words, it might answer the question, if I start with this much reactant, how much product will I get? And so that's what this example problem is that we see here. It said how many grams of nitrogen are needed to produce 38.5 grams of NH3. So we started with 38.5 grams of NH3 and we ended at grams of nitrogen. So this is what all stoichiometry problems look like. Now, we are going to introduce an idea that will allow us to do stoichiometry with gases and predict the volume of the gas that is going to be used or produced. So the relationship used in gas stoichiometry is the following. 1 mole of a gas, so 1 mole, at standard temperature and pressure, which is what we will use in our unit of study, occupies a volume of 22.4 liters. So if we're doing stoichiometry and we have a relationship where we have moles of a gas and we're trying to maybe go to liters of a gas and you have this conversion factor, you're going to use 1 mole. So 1 mole is 22.4 liters. So 22.4 liters. All right, this picture here is showing you that all of these gases, whether it's neon, oxygen, or carbon dioxide, because all of them are 1 mole, they all have the same volume of 22.4 liters because they're all at the same temperature and pressure. So that is the key new idea for this topic. This is our molar roadmap. We are going to practice finding a path on the molar roadmap like we did in the last unit. So this one says, with your finger, trace the path to convert from grams of a given, so that's where we're going to start, to liters of an unknown. So if we start at grams of given, we're starting here, and we're going to liters of an unknown, we're ending here, and you must follow the arrows of the molar roadmap. So we have to go from grams of given to moles of given. The next stop is here at moles of unknown, and then that takes us to our final stop, liters of the unknown. So everything else on the molar roadmap for this problem we would ignore, and we would just follow that path from grams to moles to moles to liters. All right, feel free to pause this next one and try it on your own. It says to convert, trace the path from liters of given to moles of unknown. So we would start here at liters of given, ending at moles of unknown. So our pathway would follow the molar roadmap here through moles of given in the middle, and then we'd finally end at moles of the unknown. So we would not use any of these other terms. We would just use this pathway that I've circled right here. All right, one more. I want you to try this one again on your own. Trace the path to convert from liters of a given to particles of an unknown. So starting at liters of given would start us here, ending at particles. Oh, this was a typo, y'all. That should be particles of the unknown. We would be ending down here because everything on the right-hand side should be the unknown. And so we would end down here. We would have this kind of zigzag path, unused, 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 unused. All right. Again, the numbers that we use in each conversion factor. The ones in white are old news. The first one, if you convert between grams and moles, use 1 mole and the molar mass of grams. The second one, old news. If you convert between moles and moles, this one's my favorite, I said it 8,000 times, you'd use the mole ratio, aka the coefficients. If it's moles to moles, you use the mole ratio. The new part of these problems is the one in red. If you convert between moles and liters, we use 1 mole and 22.4 liters. All right, so we are ready to go. We are going to try a couple of practice problems together and see how these work. So, number 1, Hydrogen and oxygen combine to form water at STP. A is going to be write a balanced equation, and B, what volume of oxygen is needed to make 20 grams of H2O. All right, so let's start. Hydrogen and oxygen combine to form water. All right, hydrogen and oxygen are both diatomic elements, so this is going to be H2, and that is a gas, plus O2, also a gas. Combined to form is going to be our arrow, and then water. In this case, y'all, water is probably a gas, but it could also sometimes be a liquid. So I'm going to say gas/liquid ? It doesn't matter though. It's not going to affect how we solve the problem, so I'm not going to worry about it. Part B says what volume of oxygen is needed to make 20 grams of H2O. All right, what we're going to do first is we're going to develop our strategy. We did this back in Unit 6 Stoichiometry. So where are we starting? We are starting with the given 20 grams of H2O. All right, if you look at your molar roadmap, what comes after grams of your given? Well, if I kind of use this one as my guide, I'll erase all my marks. We are starting at grams of given right here. Okay, what comes after that? Moles of given. So that's what's going to come next, moles of water. Okay, and I'm going to go ahead and start thinking about where we're ending. We're ending at volume of oxygen. So back on our molar roadmap, we're ending at volume, which is liters. Okay, so the next steps that I need to go through, I've already done that one, I've done that one. Next step, I need to add moles of my unknown, and then finally liters of my unknown. And my unknown here, remember, was oxygen gas. That was the chemical. All right, so I'm going to go to moles of oxygen, O2, and then finally liters of oxygen. All right, let's set up our conversion factors, our dimensional analysis, and get to work. So 20.0 grams of water is our starting point. You have no choice in life. You have to bring the unit down diagonal, gram of H2O. And whatever's next in your strategy is what goes next on your dimensional analysis. That's moles of H2O. Remember, it's whatever's next in your strategy. Okay, you have no choice in life. That unit has to come down diagonal, moles of H2O. Then you ask yourself, what's next in your strategy? Moles of oxygen is next. And finally, liters of O2 is next. So I'm going to bring down diagonal moles of O2, and liters of O2 is where I end. All right, we are going to look at one conversion factor at a time. So moles of H2O to grams of H2O. Remember, if you have moles to grams, you use 1 mole. And down here is going to be the molar mass of water. Well, the molar mass of water is 18.02. Okay, the next conversion factor over is moles of O2 and moles of H2O. Well, when it's moles to moles, you use the coefficients. And I am just now realizing that I forgot to balance my equation. So I need to go back and do that. I must balance the equation. That's what I'm putting a box around in orange. It is not balanced. Let's see. Oxygen starts with 2. So I need to end with 2. I need to put a 2 in front of H2O right here. And then that means I need a 2 in front of the hydrogen so that it is 4 hydrogen on each side. All right, so now in this conversion factor here, mole to mole, I need the coefficients from those chemicals. Well, the coefficient of oxygen is a 1 here, understood 1, so 1. And the coefficient of water is a 2, so 2. All right, fabulous. Last conversion factor, liters and moles. This is the new thing. This is it. This is the only new thing in this topic. 1 mole equals a volume of 22.4 liters. All right, we are just about ready to calculate. If we cross out our units that we set up correctly to cancel, they're gone. Okay, the only unit left is liters of oxygen, and we just need to figure out the number. All right, so the math here, remember we multiply across the top and divide by the bottom. I'm just going to put a little note here that this is what you would actually type in your calculator. If you know how, go ahead and pause the video and convert it or calculate it. So it's going to be the numbers across the top multiplied, so 20.0 times 22.4, and then we divide by the numbers on the bottom, divided by 18.02 and divided by 2. So type that in your calculator, pause if you need to. You need to practice. All right, we get 12.4. So 12.4 liters of oxygen gas is my answer. It's 20 times 22.4 divided by 18.02 and divided by 2. All right, let's move on to number 2. Number 2, potassium chlorate is produced when potassium chloride and oxygen gas react. Part A, write the balanced equation. Okay, let's see. Potassium chlorate is produced. That means that it's going to be on the product side. So KClO3. It's produced when potassium chloride and oxygen gas react. So my reactants are going to be KCl and oxygen. And oxygen is specifically the gas that we are concerned with. So I'm going to label oxygen as my gas. All right. The stoichiometry says how many moles of KClO3, that's our question mark, our unknown, are required to produce 9 liters of O2. That's our given. So let's work out our strategy. Strategy starts with your given. We have 9.0 liters of O2. All right, wherever you start on the molar roadmap, your first stop is going to be converting what you're given to moles. So I know that I'm going to go to moles of O2 next. The next stop on the molar roadmap is moles of your unknown. So that's going to be moles of what it's asking for. It's asking about KClO3. And then what I notice is that I have made it to this last part. I am at what it asked for, which is moles of KClO3, so I'm going to stop. All right, let's do our conversion, our dimensional analysis. So I start with my 9.00 liters of O2. I bring down liters of O2, and moles of O2 goes on top. I bring down moles of O2, and I go to moles of KClO3. All right, let's see. Moles to liters is our new thing this unit. 1 mole of a gas is 22.4 liters. The next conversion over is moles to moles. When it's moles to moles, we use the coefficients. And I'm realizing, again, I forgot to balance my equation. That's okay. I didn't need it yet. Now I do, so I'll go back and balance it. Oxygen, I see, has what I call the 2-3 split, or the 3-2 switcheroo. So in front of the 2, I need to put a coefficient of 3 in front of the oxygen. And in front of the KClO3, I need to put a 2. But I now have 2 potassiums and 2 chlorines over here on the product side, so I need a 2 in front of KCl on the reactant side. All right, so KClO3 gets a 2 in the dimensional analysis, and oxygen gets a 3. Perfect. All right, we are ready to calculate. So again, I'm going to make a little note down here that this is what I would type in my calculator. Multiply the numbers across the top, so that's 9.00 times 2, and then divide by the numbers on the bottom. Divide by 22.4 and divide by 3. Make sure you're following along. Type it in your calculator to practice. And we get 0.2678. So my answer with 3 sig figs is going to be 0.268. And the final unit is moles of KClO3. All right, great job so far, y'all. Let's do one more. We are going to look at sodium reacts with sulfuric acid in a single replacement reaction to produce hydrogen gas and sodium sulfate. Let's see if Miss Hammer remembers to balance it this time. So sodium reacts with sulfuric acid, H2SO4, to produce hydrogen gas. If it specifically says it's a gas, label it a gas. And sodium sulfate, Na2SO4. All right, studying this and thinking about balancing it, looks like everything is balanced except sodium. Sodium on the reactant sides needs a coefficient of 2. There are 2 sodium, 2 sodium, 2 hydrogen, 2 hydrogen, 1 sulfate, 1 sulfate. Everything looks good. All right, let's set up our strategy. The question says how many liters of hydrogen gas will be produced. So the end of my strategy is going to be liters of hydrogen gas when 16.8 grams of sodium reacts. So I'm starting with 16.8 grams of sodium. Okay, so I'm starting all the way over on the left-hand side of the molar roadmap with grams, and I'm ending on the upper right with liters. So in the middle, I know I need to go through moles. So that's going to be moles of Na, and then I'll convert it to moles of my unknown, which is moles of hydrogen. All right, let's set up our dimensional analysis. We are starting with 16.8 grams of Na. Bring down grams of Na and convert to moles. Bring down moles of Na, convert to moles of H2, and bring down moles of H2 and convert to liters of H2. All right, one conversion at a time. Moles to grams, we use 1 mole and the molar mass. The molar mass of Na sodium is 22.99. The next conversion over is mole to mole. Well, looking back at our balanced equation, the coefficient of hydrogen is a 1, so I put a 1 in front of moles of hydrogen, and the coefficient for Na was a 2, so I put a 2 in front of Na. All right, the last conversion over here on the right-hand side is liters to moles. This is the new thing. So 1 mole is 22.4 liters. All right. Feel free, if you feel like you know what to do, to pause the video here. If not, this is what we would type in our calculator. Top numbers multiplied together. So that's 16.8 times, remember you can skip the ones, times 22.4 divided by 22.99 and divided by 2. All right, so let's type that in and see what we get. 16.8 times 22.4 divided by 22.99 and divided by 2. I get 8.18. And that is liters of hydrogen. That's the unit that was left. All right, that is our last example. I hope this was helpful. Main idea, remember that if we're talking about gases, 1 mole of a gas occupies a volume of 22.4 liters. Thanks for watching. See you next time.